Okay, final session, Spack, here we go.
Okay, so just a few information on slides and, trivial stuff. All the slides are available on GitHub in this repository, and they are on GitHub pages. So whenever you want to look at them, they're already online. And I will use throughout the talk a container which is published on Docker Hub. So Alalazo, Spack, CSCS, Software Management 2019. It's huge because I put all the binaries of the things that we are going to build during the demo. It's 4 gigabytes. You can get more or less, let's say, pristine one from Ubuntu, which is 400 megabytes, but then you have to wait for things to build from sources. Instead, in the other one, I already basically packaged binary artifacts to be fast during the demo. So that's what I wanted to say up front. So, my name is Massimiliano. I work at EPFL in a group, CETAS, that basically manages the HPC clusters of a university. And there, I take care of software deployment on the cluster. And it happened that because of that, I started to be a co-contributor to a package manager, Spack, which will be the topic of today. So the line of thoughts for the talk I'm going to give is slightly different from what we usually do. What we usually do is focused on deployment. Today, I'll try to take another path. So I will give you like an impression of all Spack basics so that you can know how to install, uninstall stuff, query things, and whatever. I'll show you how you can write a package so that you can move from being a basic user to being a packager, I assume of your own project or whatever. And then I'll show you how you can profit from Spack when you're developing to basically help in your workflow. And finally, if time remains, how you can deploy software for either other users or your fellow developers. So that's the idea. And at the end of each part, I'll show a quick demo to exemplify what I talked about. And please interrupt me if you have questions. But before starting, why are we even here talking about package managers? That's the real first question. And the answer that I can give you is because scientific software is complex. So what you see here is basically an image that shows a very well-known finite element library, DL2, along with all its dependencies. And I would say that what we've talked about so far deals with a blue box, the thing that you are developing, like Git to manage your own sources, Jenkins to test, DL2 in this case, it could be HPX. I think they are more or less the same level of complexity. But of course, all the red boxes must be there if you want to start developing or if you want to develop your software. And what was done up to not so long ago, at least at the sites I know of, was that people would go almost manually through all the red boxes, build things. It's tedious, it's error-prone, and it doesn't scale. And on top of that, which is, let's say, the problem you face when you develop a single application, there is also the combinatorial explosion that John talked briefly about. So in HPC, there are peculiar requirements which are somehow tied to performance in that you want binaries to be optimized for the machine they're running on, not like generically optimized. And they're also tied to the fact that many scientific libraries or applications can be configured in different ways. And usually, you have to deploy those applications with a certain number of configurations that must coexist with each other in the same file system. You want to install them for a certain number of targets, use a certain number of compilers. And that, of course, leads to a lot of combination that you have either to deploy if you are like a user support group or test if you are a developer. And as I said, installing manually, it's not an option. I think I don't have to convince this audience of that. But even using script, I would say it's only slightly better, because scripts are usually very context dependent. They work well for the task they have been written for. But if you move to another machine, or if your environment changes, usually they need, let's say, to be tweaked. And they don't work usually out of the box. So they can automate deployment or test on this machine right now for this configuration, but they require a maintenance effort that will increase in time. And just to give you my perspective on the thing, this became really tedious when I started working on that, and I didn't have a proper package manager, because if I thought, like, what if I abandoned those two requirements to have optimized the software and to have multiple combination of stuff that must coexist in the same file system? Well, if we abandon those two requirements, which are typical of HPC, we have distros package manager, which are working very well. You just say, please install whatever I need as a dependency. Those happen to be, for instance, more or less the dependencies of HPX, and then you get things installed and you can start developing. Our claim is that scientific software must be that easy to use. And that brings us to the first part. So what is Spack? Well, I'd say that Spack is basically a package manager of that kind for HPC. It has been designed with simplicity in mind. So to use it, you just have to clone the latest version from a repository, or extract a tarball if you want to go with a tagged version, source a setup file, and then you'll have Spack in your path, and you can start using it. For instance, if you say Spack install HDF5, it will download, build, and install HDF5 along with its dependencies. And normally, it will build from sources. So it will go on the web, fetch the tarballs, start building things, and install. I won't go into the details here, but you'll see later when I will be giving the demo. But Spack can also create binary tarballs of its artifact that can be reused later if the configuration you want to install is already in a binary format. Spack is also an open source project and a community project. It started at Livermore. The lead developer is Todd Gamblin. The code base is hosted on GitHub, and it's dual licensed, Apache 2 and MIT, and you choose which one you want to use. Why it's dual licensed? That's because we want vendors not to be scared by GPL license or LGPL license. So we want vendors to be able to buy in the tool or even contribute back without any fear. And here you see, here you see like the main repository, the one of the Spack organization. Also, it's already used worldwide in production. Spack is the tool that will be used to deploy the software stack in the exascale computing project, and that's already been decided. Here you see session on read the docs for 1 month. It doesn't tell you much, or numbers are not important. The only thing that I want to stress is that it is used worldwide. Of course, you see like a big blue dot around Livermore, but it's also used in Europe and at many centers worldwide. At EPFL, we use it in production since 2016 to deploy our software and generate modules automatically, and so on. And another thing that is worth saying before we start with more technical stuff is that Spack has a huge community. I think we just passed, a couple of days ago, the 400 contributors. And of course, most of them are for recipes, for packages. We have Slack channels to discuss things and so on. And there is there are ongoing efforts by the community to disseminate best practice or training. And the next event are like an half-day training at ISC, which is already confirmed. And if it will be accepted, there will be a one-day training later in the year at Supercomputing. I think there has just been a two-day training given by people from Livermore at Riken in Japan, because Spack will be the tool they will use to deploy software on the post-K machine. Okay, so far for, let's say, the project and the community. Let's start to talk about more technical stuff. I told you that one of the problems in HPC is basically dealing with the combinatorial complexity that arises. And I claim that Spack can do it, but how it can do it? Well, I'd say that Spack manages this complexity by combining, let's say, 3 different features into a coherent design. And those 3 features are 1, user-facing, 1, packager-facing, so people write packages, and 1 is basically inner working of Spack and its algorithms. So the first feature is a domain-specific language to describe what you want to install. So Spack provides a syntax, we call it the SPAC Syntax, to describe user needs, mainly from command line, but also from configuration files. And if you look at the first line, for instance, the user specified that he wants HDF5 at a particular version installed with the at sigil. So HDF5 at 1.10.1 means please install this specific version. And that's the constraint that the user cares about. Similarly, you can specify which compiler to use with a % sigil. And you can activate or deactivate options. That's the next line. Like I want HDF5 with support for szip. And that's what we call variant. In this case, it's Boolean, so the syntax will be a plus if it is active or a tilde if it is deactivated. And you can also like inject compiler flags into the compilation, meaning that each CPP file, each, let's say, compilation unit will be compiled with -03, -f loop block. And you can also target different backends. There is one thing that is not on the slide, an additional sigil, which is the caret, which basically makes the syntax recursive. So you can specify dependency if you care about that. For instance, you can say, we'll see later, I want to install HPX depending on Boost 168 because I want to fix the version of Boost underneath. You do that with a caret, and basically the syntax becomes recursive because you have to specify another package there, and you can use more or less the same sigil. So the first feature that makes it possible to manage complexity is this domain-specific language that you use to specify your needs, no more and no less. The second feature, is the way we model packages and recipes via directives. So in this case, we are in the role of somebody writing a package. And when we model the different possibilities that this package offers, to be clear, we saw yesterday that EasyBuild needs one file for each, let's say, its concrete configuration. So one file for OpenBLAS at some version configured in some way. Instead, I want to stress that in Spack, OpenBLAS will just be a single file, and that's where directives kick in. In this file that describes how to build OpenBLAS, you can specify different versions, each one with their own checksum. You can specify different variants, which can be active or inactive. And you can even rule out subspaces of a combinatorial space if that makes sense. So for instance, the conflict directive at the end basically means that in a certain version range, this package can't be built with Intel 16, so that if a user asks to build with that specific compiler, you will have an error message that says, no, sorry, this package can't build with Intel 16 in this version range. I was saying directives to model the package are great because basically we are fighting combinatorics with combinatorics. We are building up a combinatorial space from the basic components. In this case, we have 2 versions and 2 variants, and we have already 8 combinations because they multiply, and that's not accounting for compilers or other stuff. So the second part to tackle this combinatorial problem is directives model when you write packages. And finally, there is our constraint resolution algorithm that in Spack parlancy is called the concretizer, that basically takes, on the one side as input, the user request what you want with your constraint, the one you care about. On the other side, it takes the recipes, so how that package is modeled, and basically fill in the blanks, because of course you won't specify each and every detail. So this constraint resolution algorithm has heuristics to decide what to put in HDF5 if you didn't specify if you want it shared or not, if you want as zip or not. And basically what you get in the end is a directed acyclic graph, which represents the exact thing that will be installed at this time. This graph will have a lot of metadata on both nodes and edges. And basically, you can hash this graph. And what the concretizer does is to pass from an abstract request that the user is making, an abstract SPAC, we call it, into a concrete configuration that can be installed. I said this graph can be hashed. And in fact, we use this hash in the installation prefix of each package to make various configurations coexist with each other. So Spack doesn't need, of course, administration privileges to install because it installs by default in a folder that is within Spack itself, but you can configure it to be any way you like. When Spack installs things, it basically creates installation prefixes that are unique and are based on the hash of the graph that we've seen before. And finally, the last thing that I should say is that not only we can deal with real packages, say OpenBLAS, it's a real package, we can also deal with versioned APIs of things. So you can declare a package to be depending on MPI or even on MPI 2, and you might have other packages that declare that they provide MPI version something. And basically, this permits to switch in and out different API-compatible but ABI-incompatible packages during the build. So that's another, let's say, level of abstraction that we can manage. And we basically use that because it fits with reality. HDF5 depends on MPI. It doesn't depend on a particular implementation of that. Similarly, for packages that depends on LAPACK. And LAPACK is particularly, I would say, it's a good example because it could come in many different ways. Nonetheless, I mean, like split into two libraries, liblapack and libblas underneath, or like OpenBLAS, which is a single physical library. But nonetheless, a package that depends on LAPACK calls should be able to be built with all the LAPACK compatible packages. And that's basically what we can manage. So that's how we manage complexity. So second question, which information do we store when we install thing? We basically store every information of each package you already installed in a central database, which is nothing but a JSON file. Usually it lives in the path that you see down in the slide, below in the slide. We store information like if the package was an explicit request of a user, or if it was implicitly pulled in as a dependency of something else, the installation time of a package, stuff like that. And this is basically a central database. Not only we do that, but we also preserve provenance, let's say local information, local provenance, in each installation prefix of each package you install. So here, for instance, I installed HDF5. And when you install with Spack, you get an extra hidden directory, .spack, in the installation prefix. And you can see that we archive relevant files, like the config.log, as this one is an AutoTools package. It could have been like the CMake cache if it was a CMake package. The complete environment, a dump of the environment that was used during the build, all the build output, so all the logs of the build output, the recipes. What you see in repos are the recipes that were used to build this package. And spec.yaml is basically the graph, the concrete graph, in a YAML format. And from this distributed information, we could regenerate the central database. So if anything happens to that, there are commands to say, OK, grab all the local information and reconstruct the database. It's not frequent, but it's also safety measures. Sometimes, GPFS flickers and you get inconsistent state. It's good to know that you can reconstruct the central database with that. So once you have a database that you can query, of course, you can start build a lot of tools upon that, upon querying the database and performing actions on the result of the query. So for instance, we can check beforehand what will be installed if we use a specific formula. Here I'm saying SPAC spec minus capital I means basically show to me what is already installed. And then I say HPX using standard 14. And what I see is that, OK, this is my request. And here I have basically a flattened version of a graph output to me, where the plus means, OK, this is already installed. The minus we see in HPX means, no, HPX needs to be installed still. So you can make queries like that. You can query what you have already installed. For instance, if you say Spack find zlib, it will tell you all the versions of zlib that you have installed. You can do more complex things like asking what I installed with this compiler, what I installed that depends on boosted this version with this option, what I installed since a month ago. So we use things like that to automatically generate month of the day to be shown to users when we deploy stuff. Like, hey, this package has been installed. They stay 1 month and they get deleted. And you can, likewise, uninstall thing with more or less the same query. Another important point is our shared libraries, and here I'm talking specifically of like compiled application or libraries found at runtime. What we decided to do is basically to use rpath for everything. As we can manage the complexity of things and we can rebuild different stuff linking to different configurations, we want things to work the way they were built. And so we decided to basically set rpaths during the compilation phase for everything. And we do that by basically employing a thin wrapper within Spack that injects the proper compiler flags. It doesn't do only rpath, it does a few other things like injecting the flags, what I showed before, that you can say, I want to install this library, and by the way, always use -03. We inject that flag via the compiler wrapper. But this is, let's say, a design decision that is worth knowing. Spack builds everything using rpath. And finally, how can one fine-tune Spack's configuration? So there are many aspects of Spack that are configurable, and each one of them is configurable in a YAML file that is very well described in the documentation. So I won't go through all of the files. What I wanted to point out is one peculiarity. The final file that Spack will use as a configuration comes from a merge of multiple partial files, or of possibly multiple partial files that could reside in different scopes. Why we did that? We did that because this system permits to set default if you need basically from the system or from the site, and allows you to decide what a user can override or cannot override. So I hope that part is clear. If not, we'll see that into the demo. We have comment that permits you to ask Spack which configuration is currently using for some particular aspect, and ask it where does each line of the configuration comes from, really, from which file in which scope. And yeah, before moving to part 2, I would say let's go on with some demo. I hope you can see that. So I just prepared a Docker container with Spack already installed. And yeah, the first thing that usually one wants to know is which packages are available. And you can get that by just doing Spack list. And you will see that basically this will like flood your screen because there are like 3,000 something packages available right now. Oh, yes?
I just cloned the Spack repo.
Yeah.
And so I've got Spack, but it's in the, what was you said you can set up your environment by sourcing one of the files.
Okay, it should be in share. Yeah, let me check where I have Spack here. So I won't resource it because it's part of...
Share Spack setup in.
Exactly.
Got it.
And now you should have Spack available in your path. And
Spack list, that works. Okay, thank you.
Okay. Yeah, I hope everything works also, like outside of the Docker container. So I was saying, if you do Spack list, you'll get a huge list of packages. And usually, you're looking for something specific. So you can search for expression, like zlib, and every time you give an expression like that, is considered, for the sake of this command, starred on both ends. So if I just say Spack list zlib, I'll get basically 3 packages which contains zlib. Another nice feature, you will see that this command will take a while the first time it's run, is that you can search for packages that are tagged in a particular way. You can assign tag to packages, in this case, packages that are part of the exascale computing project, and you can search for them based on that tag. So you might ask yourself why it's taking like 10 seconds to do that. Basically because it's parsing all the packages and creating a cache that will be reused later if you do the same query. So if I do it a second time, it will be almost instantaneous. There are a couple of commands that the first time they are run, they basically build a cache, and they will take some seconds to run. So just, you know. Another thing that is worth knowing is that Spack will, the first time you run it on a machine, will try to discover which compilers are available and configure them for you. So if I say Spack compiler list, it will find 2 compilers that I have in this Docker machine. And if I want to know more about them, I just have to ask Spack more info on GCC. And as you can see, it tells me where the compilers are coming from. There is a modules which is empty. That's relevant if you're working on a Cray, because to use compilers on a Cray, you have to load modules. And then there will be something there if you are on a Cray, because Spack knows it has to load module before starting the compilation process. And of course, the operating system I'm on, because I could have Spack on a shared file system, which is mounted on many hosts. So it will recognize on which host you are and use the appropriate compilers if you don't ask to use something else explicitly. So another thing that is worth knowing is that Spack supports mirror. And this is like the no-trick part. I don't have any mirrors configured yet. And I will add a mirror that I prepared for this talk. So what are mirrors? They are basically paths that contain either tarball of the sources, or they could also contain binary artifacts that you can create. And that's what I did to be able to show you, like, I would say realistic examples without waiting hours for the compilation to finish. So right now, I have one mirror configured, and I have to trust, the public key that I put in there. And we have to live with a warning that the public key is not signed by anybody trustable, so you're not sure that I am who I say to be. But I didn't go that far to make up, you know, a full trust framework for this demo. OK, with that set up, I would say let's install the first thing, the first simple thing. Like, if I say Spack zlib, I will get an impression of what will be installed. I asked for zlib, and the concretizer said, OK, I will install this version with this compiler with all the variants turned on for Linux, Ubuntu 16, and x86 64. And if I say Spack install zlib, the output would be the first time a bit, I would say, like dirty. I think we need to add on that. That's because Spack is, I think this should be debug information, but basically Spack is making an index of every binary package available. It won't do the same the next time we install things, but as you can see, it found a binary package and it successfully installed zlib at this location. So that's what it did. We can go and ask, okay, I also want to install, for some reason, version 1.2.8. And that's basically the same thing. Now I have a different hash, a different version of zlib. And this is just to show you that indeed Spack can build from source. On this very simple package, I will ask to build without cache with a different compiler. So I'm asking to be verbose, so you see what's going on below. Otherwise, whatever goes on will just be in the output log. And we'll install zlib with GCC 4.7. And what you see is that I take like the sources from the local mirror, unzip it, compile it, install it. Similarly, I can install things like injecting flags. So I can do things like that, and that will create a version of zlib which has been compiled with -03 everywhere. So right now, we installed a bunch of stuff. How can we know what we install? Oh, yes.
So now you specify that you want in the CPP flex -03.
Yeah.
This information, because it was installing again from a binary cache.
Yeah.
So if I have two flags, -03 and -g.
So you have to specify them here.
Yes.
And that will be a string that you pass to Spack. That string will be used in the hash mechanism. So if you say -03 period and -03 -g, that will end up having a different hash of the graph. So they will end up producing different binaries.
Right.
Meaning, if I say -g now, I will really compile the thing, not find the binary because I didn't prepare it.
Right. And then if you do -g -03, that's again a different version, right?
No. Well, on flags, I don't know because I didn't do the implementation. But on variants, what you do is basically you impose internally a sort order. Probably for flags, they didn't go that far because the order might matter.
Yeah.
So, but on that, I need to check really the source code. I would say that for flags, -g, -03 is probably different from -03, -g, not because of those two flags, but because generally, the order should matter. For variants instead, you will see later, you will have packages in which you are permitted to give any combination of some name in a key equals value thing. So there, the order doesn't matter. So I was saying, if you want to know what's installed, you just say Spack find. And the output is kind of, let's say, useful. But for instance, we see here that the default level of details doesn't permit us to distinguish between those two things. And as I said, you can basically ask whatever level of details you want. In this case, I'm going to ask -l, which means give me a short version of the hash, and -f, show me the flags that have been used to distinguish between all the zlib version. And what you see is that the two versions that we couldn't distinguish before differ because of the C flags. So let's go on with a more complex example, HPX. Now, when you want to know what a package could provide, there is a command, Spack info. And yeah, I need probably to reduce a bit. Can you still read it? Yeah. Please tell me if it is too small. But basically, the information you get is which type of package it is. In this case, HPX is a CMake package. You get a description of the package, the on page. It has no tags, which are the version, and so on. Usually, the most important thing that you want to read are the variants. that are basically the handles that are exposed to the end user. Here we have the build type, which is one of the 4 usual build type. If you want CUDA on or off, which standard you want for C++, and so on. And I can try to do, and now I have to be very careful if I don't want to wait for like 1 hour compiling. I have to be very careful to reuse exactly what I did before. Here I'm asking, what would I install if I install SPX in release mode with C++ standard 14, instrumentation equal Valgrind, and depending on boost at 1.68.0, HPX build type release, instrumentation Valgrind. Okay, so if I ask that, basically our constraint resolution algorithm will go through the stuff and will output, well, if you want to install this thing, you basically need all those dependencies installed too.
And that's why people hate us.
Yeah?
These dependencies must all be installed by Spack, or can they be partly by the system?
Okay, so this is a thing that actually I don't cover here, but we support registering externally installed things. Then you are on your own on the dependency that are, underneath. If you install things with Spack, Spack knows what things depends on other and whatever. If you say, I don't know, Boost is already installed, then Boost will appear as a single node that is registered to be installed somewhere else, and you have to take care of that because Spack can't possibly know how you installed it. Yep.
Just a second, can I moderate with the microphone?
So are the version numbers here now, let's say, strict? So you would previously have installed with Spack Boost 1.60. So would it now then, okay, it probably will work with Boost 1.60, or will it need to install that Boost 1.68?
What do you mean? So the concretized, it's given that you asked for Boost 160, okay, Boost is the wrong thing because we asked for a specific version. But let's say, given that you asked for HPX, okay, and that Spack knows that HPX depends on HWlock, it says, okay, then I'll install HWlock at 2.0.2 using some heuristics. So the heuristic now is very simple. If you don't specify, we use the latest version that doesn't conflict with you.
If you would have had installed an older version, would it then use that, or would it pull the newest one?
That is planned, but not yet there. So right now, the concretization algorithm doesn't take into account what's installed and what's present in the binary mirrors. An improvement that we want to make is that it takes that into account to prefer things that are either already installed or already packaged as binary, unless you specify otherwise, unless you say, hey, I don't want that, or I want a specific version and it's not in that format. But right now, no, the heuristic is quite simple, and it's basically use the default that are prescribed in the packages for variants, and use the latest version if there are no further constraints in the package. So if you have Boost 160, or let's say if you have HWlock 2.0.0 installed, this will still install the newer version.
I also have one question about the architecture. So
okay. May I just start? Do you need to? I mean, is your question related to this graph? Otherwise, I'll start the installation of HPX, which will take 1 minute, and answer your question. May I go?
Yeah.
Okay. So hopefully this will work.
Minus V would have been you. Oh, okay.
Oh no, because it's this thing is basically taking binary tables that I generated before to be fast on the installation. You see that boost takes like, 10 seconds. In reality, it took hours to compile this thing, and then I packaged all the binary to be able to show you that I can go through.
Are those binaries specific to your machine, or are those binaries, I mean, they're specific to the compiler version, the boost version,
Exactly.
blah, 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 and does it also take into account the architecture and stuff? So if I trust, is this because you trusted the mirror?
Yeah, because I trusted the binary packages. I signed the binary packages with my GPG key.
Okay, that was where you did,
Exactly.
you put that mirror in. So if I add that mirror to here, now if I'm using the same processor and...
You could reuse binaries, and that's the idea. So that would be a thing that I would have said at the very last. But one of the things that we plan to do in the Spack community, I think it should start to be available by end of this year, is to build around Spack an infrastructure to serve both sources and binary packages. Of course, not for all combinations, but just for relevant packages in some combination, in some widely used combinations, so that you will have mirrors somewhere that you can trust because they are maintained, I don't know, by Livermore or by Argonne or built by them. And you can prefer them. And when you install, if you install usual stuff like OpenMPI, you will get it optimized for your cluster, but also you don't have to wait for the build to finish because your configuration is, let's say, widespread enough that we already have a binary for that. And another thing that I wanted to say as we are talking about that, by the way, HPX is there and it's finished. One thing that I wanted to say is that Livermore is working with a company in that respect, which is called Onyx Point, so that not only you can build things for, let's say, usual cluster like we could have at EPFL, but also for top-level machines for Cray. They're working on a GitLab runner that can basically change the user ID and impersonate you so that they won't have security issues. You basically send a build job on the compute nodes, and they know exactly that it's that specific user that issued the job. I don't know really the details, but they're working on that, and they're pretty close to finishing that thing. It started to be able, I think, to produce those binary packages for Cray machines or top-level machines, but I think it could probably turn out to be useful in a generic testing framework, because basically that's a runner from GitLab that can set the UID, enter the queue as a user using some account, and run somewhere.
For versions, like you say, okay, Spack install, HPX, blah, blah, blah. Now, I noticed that in the config of things, okay, you didn't have one for HPX because we've got version 1.1, 1.2, 1.3, and you can specify a hash for different versions.
Yeah.
Can I, if I'm working locally, can I say, use this branch with boost 1.8 and blah, 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 and then do another one with that branch with boost 1.8 and blah, blah, and then just sort of leave it running in the background? And
Yeah, you can do that.
because I didn't notice if you can specify GitHub or Git repositories.
That will come later in the second part, but you can do that. And you can even, let's say that you have your own specific branches. I will show you that what will probably happen is that in the built-in repository, those won't be available because they don't matter for everybody. But you can have your own private repository, inherit the recipe from HPX from the built-in one, which contains everything, and you just add those two versions you care about. And when you install, you say, I don't know, install john.hpx, supposing that you name your repository John, and then you're done.
I had one question in the queue. So It's related to John's question. So
Okay.
how do you see the architecture? You just had a list in Spack, HPX, and you had the
So
you just had Linux, Ubuntu Linux, and you
okay,
didn't see how do you see
for the operative system, we rely on a Python package which is pretty well done. I think the name is distro or something like that. So what it can automatically detect is pretty fine-grained. Right now, in the main line, for the target, we just use whatever Python platform module can do, which is not that fine-grained. And there are like ongoing work to have a better detection of the architecture. What do I mean? As you have seen, here the architecture has been like discovered as x86-64. What we would be able to do is to be able to say like Skylake, Ashwell, or things like that. In reality, what happens is that at sites like ours, I just add I think, a 5 lines path to Spack to be able to override the target so that I can say, okay, I'm running on a node with this architecture, running on a node on the other architecture. What we want to do instead with the mainline Spack is to be able, on the one side, to auto-detect in a finer way the architecture we are on. On the other side, to have a database that maps usual optimization on all the architectures to, let's say, compiler flags or whatever, so that you can cross-compile. Why is that? Because, you know, it's good to compile a NAST, but probably if you have a powerful node that you use for computation, it's not the best use of the thing you can do to run build jobs repeatedly on that. You can very well buy cheap nodes somewhere and say, hey, I want to build for Skylake. You get your artifact, and then you use them. That's the final idea. So what I wanted to show you is that indeed, and I'm going very long with that, so I don't know if we are going to cover everything. Indeed, we set our path. So this is just wrapping from one of the library in libhpx, and everything is our path. And if I do something like LDD of the library, I can show to you that I don't have LD library path set. But if I do LDD of the thing, and I probably need to go, sorry, if it is to even one more, you see that there are no not found here. And that's because we basically put into the binary all the paths where the library has to search for dependencies. And I think I'll gloss over an installation or just show you one. Like you can say Spack and install things. In this case, zlib. Let's uninstall the old version. And like what happened is that you will be queried. Oh, I'm going to uninstall that thing. Usually, whatever command might be dangerous, like removing stuff, you are prompt yes or no if you want to proceed, and you are given a summary. In this case, you can proceed. If you want to script things, you can say assume that yes to everything. And you can even do things, assume yes for everything, and please uninstall everything that I built with GCC 4.7. So when you give us, in context like that, a specification without a root package, you can read it like compiled with GCC 4.7. It's an anonymous spec. It means anything that matches that, anything that was compiled with GCC 4.7, there should be only zlib in this case. And in fact, it says, OK, I successfully uninstalled that. You can do things like that, like at your pleasure. Uninstall anything that depends on Boost 168. Uninstall anything that was built for this target. Or find anything that was built. And the last thing that I want to show you before adding a compiler, I need to install it. You can also bootstrap compilers.
Whilst you're waiting for that, if you can bootstrap compilers, can you bootstrap compilers for cross-compiling as well? I mean, would anybody have already set up recipes for things like Raspberry Pi compiler setup? And
So Raspberry Pi, I don't know. But I think you can do that.
Okay, I was hoping you'd say, yeah, everybody does that all the time, because then I'd just use it. If I have to do it myself, then time is too short.
No, but I think you can do that. I'm pretty sure that they already tried ARM or things like that. Yeah?
Do they still have GCC3 F77?
I don't know. We need to. Please don't ask me out of 3,000 packages if there is still version X of package Y, because I don't know. But
just because you bootstrap GCC 8, and I'm asking for, I'm not sure, was it 3 or 2?
so let's look at the GCC recipe.
No,
Apparently, the first one we have is 4.5.4, and even there, I don't know how much these days this version has been.
So there is no
No GCC3, no.
For F77 is what I need.
So you need GCC3 for the Fortran compiler.
I think so. It's the 3 that the last version that.
May I say shame on you?
It's not
Sorry.
me using Fortran 77, but are we
I know, it's just a joke.
That's what I told them 5 years ago. They don't care. They have such a large code base. They will never port that to something more modern.
But yeah, in that case, probably they should really ship their own environment because, yeah.
With my own spec, submit in case
So
anyone else
yeah.
is in a poor situation like me.
Or find different users, I would recommend.
So as I was saying, after we install the compiler, we can also add it to the list of non-compilers. And now, if we ask again information, so maybe I could, no, that was the wrong thing to do, sorry. If we ask again information, yay. We see that the most recent GCC comes from Spack, and we see it from the path, which is pretty long and not like in the system path. So if there are no questions, I'll move on with the second part of the presentation. May I still run up to 4:30 if need be? Yeah, well.
As far as CSCS is concerned, you've got till midnight, and
Okay.
when people have had enough, they just quietly leave the room and
Okay.
sort of wave goodbye.
Please,
You just carry on as long
exactly.
as you like,
Please
right?
feel free, to go. That's just to know if I have to shorten up on some topic.
If people have trains to catch, they'll just leave.
Okay. So the second part that I wanted to show you is, well, right now we covered the basics. You should have an impression how to use the package manager. The next part is how you write your recipe, how recipe is written. So the first thing is, how does Spack store those recipes? Well, recipes are just Python classes. They need to have some mandatory parts, like a doc string, which is the package description, the home page, the URL, which we use to fetch version or things like that. And then it's up to you to describe the package as you want with different versions and their checksum, with variants and with dependencies. So another thing that I wanted to stress is that we don't just care about end users, we also care about people that write packages. And therefore, Spack ships with a lot of subcommands that are meant for packagers. You can easily create a new package if it's not already there, starting from a URL. So Spack will download a tarball, inspect it, and basically create a stub package for you with a lot of fixpins telling you what you need to put there in order to have a fully fledged package. You can easily modify an existing package. You can say Spack edit HPX. I think we'll see that afterwards. You can scrape for new versions, of course, if a website of the package permits it. Spack will try to check which versions are available and things like that. How do you declare package versions, and how does Spack do fetching of a version? This, I think, replies to your question. So usually, you have a URL that is specified pointing to some stable tarball of the sources. The usual way in which we fetch version, for instance, you see here version 6.4 with this checksum, and here we have version 6.3. Basically, those URL are passed through regular expression, and we do matching and substitution. So if a URL matches some regular expression and we can extract a version from it, we substitute the new one and we get the new URL. This is the default. So for any sane, let's say, way of distributing packages, meaning like, I don't know, 80%, 90%, this works. Then if you still maintain old versions that are stored at another location completely, you can override the URL just for that version, specifying it in the directive. So in this case, 6.4 will look at QE blah, blah, blah 6.4, but 5.3 will go to this specific URL. It's possible to support Git repository. Usually what you do is basically specify the Git repository or the Mercurial repository or the Subversion repository there. And then you can have versions that are tied to branches or tags. Or even commit hashes if you care about security, like a tag is something moving or might be something moving, a branch is surely something moving. If you care about giving your user a specific, let's say, version of the code, you can also use commit hashes.
I actually realize now that I see it that that's not what I want after all. It's more complicated. What I really want is, I want to build in my tree, my version of HPX on my branch, and I want to build it the way I build it all the time. But I would quite like to say to Spack, right, I need boost 1 point, and I need TC malloc, and I need J malloc, and I need...
Okay, you're always one section ahead.
I want all of those things. Now, just give me the CMake parameters that I need to paste into my CMake config for this build to pick up all that, because you've installed them into Spack / and they're all there.
Okay. Okay.
But they're in your Spack repo, and what I want to do is link against them. So
okay, so that thing is not there yet, but we are working toward it. What we can do right now, and that will be part 3, is install in a convenient way all the dependencies for you. So if you say, I want Boost configured in this way, I want tcmalloc, I want whatever, we can install all your dependencies in a sort of development environment, and then you can use that for your own development. What we need to add is, as you said, some way to help you bootstrap in the process and then give back control to you.
What I need is like a SPAC info and then the list of all the things that I depend on, and then it just dumps out the equivalent of what I would paste into my CMake invocation, which would be a -d root directory for that and a -d.
That's the only part that is missing right now in develop, the CMake invocation.
Awesome, yeah. Okay, I'll help you with that then.
And yeah, so the last part I was saying, if need be, so for weird cases where the URL is changing so fast, or let's say is so peculiar that you need it, you have this function that you can override, and that basically permits to do any kind of computation you want. The semantic is that you get the version that has been required, and you should return the correct URL. So it is just needed for a few packages. And the point you should take home here is that for, let's say, usual workflows that works most of the time, we try to be very compact and intuitive. You give us a URL, and then you proceed giving versions, and you don't care. If need be, if there are weird cases at the expense of some additional complexity, like overriding a function, you can be much more flexible. Like you can do any computation you want and return the URL that you need. Well, I could skip that, but basically, there are ways, for instance, if you need to change things that are one level upper or two level upper, or you need to start searching for versions at some earlier point in your URL, you can do that. Basically, the list URL is where you start searching. The list depth is how deep you need to go searching. And how do the things combine? When you specify that in a package, your user can say, hey, Spack checksum MPICH. Spack will say, I found 34 versions of MPICH. List, how many would you like to checksum? And you can even say Spack checksum MPICH and give some of the versions. And Spack will basically download the things, checksum, and if it's not there already, you can start a PR with a new version or things like that. Those are basically conveniences that we give to user. Yeah. Then, if you want to expose configuration options to your users, you can do that with variants. Variants can start as simple as a Boolean variant, like this one, which can be either true or false. This is basically the variant shared we've seen before on HDF5. The description usually is something like builds, shared libraries, or things like that, and then that can be active or non-active. The way it's used within the recipe is that you can query on what the user asked. So you can say, if plus shared is in my specification, then go on and append to the configure arguments -- enable shared. Otherwise, do some other thing. And that's basically composable in the recipe of the package. Again, what your user will do, your user will ask for something, it will give a specification, or maybe the concretizer will fill in the specification for him if he doesn't care. And then at some point, you will end up in this code, and you can take decisions based on that. Variants can be much more complicated than that, if need be. You can have the logical equivalent of an enum, so choose one value among many. That's what we call the single-valued variants. Like in this case, you have a variant thread. The default is none, but it can have 3 values, and only one can be chosen at one time. It can be pthreads, OpenMP, or none. And you have to explicitly, in this case, take care of a value, even of a none value. And finally, you can even go like astray, I would say. You can have things that allow any combination of those two things, or they can even be more complicated. But as I said, the more flexible you go, the less use cases you'll find. Usually variants are either, I would say that there are a few of them which respect this logic. That's why we made like convenience function to express this. If it was not clear, this variant staging can be either none, which is allowed not to have anything. It represents the empty set. Or it can be FlexPath, or it can be data spaces, or it can be both. And here the order doesn't matter, because you basically activate both. It doesn't matter if you say FlexPath and data spaces before each other or not. Finally, a few, yeah.
Do you have restrictions for variants? So I can imagine that there might be variants that can only be enabled if another variant is enabled.
So that's like a requirement, an issue open on that, but currently we don't do this. You might ask why we don't do this, because that complicates a lot the SAT solver at the moment. Because basically you need to backtrack on which decision you made to know if a variant is enabled or not. So we don't have variants which could depend on other variants. But on the other hand, we have conditional ways, which is the next slide, to specify dependencies. So when you specify a dependency, you basically use this directive, depends on. Here it's like a snippet from the HPX package. We have a variant, which is the C++ standard that is used for HPX. And we know that HPX depends on boost. And if I say HPX depends on boost, this is a true statement. I mean, as it is. But I also know that depending on which standard I want for HPX, I need to enforce the same standard for boost for compatibility reason. And we can do that in a conditional way, as you said. So here I say, OK, it depends on boost. And here I further specify the thing, like, OK, it depends on boost compiled with C++ standard 98 if I wanted to compile HPX like that. And we can do things like this also on other variants. So
there is no shortcut for this saying CXXSTD equal the same.
No, no. There have been talk to have what they call variant forwarding, but it seemed like the use cases are, let's say, few enough that it hasn't been prioritized yet. Because in a case like that, you could say, OK, I know that boost has the same variant. I know that by convention, we adopted the same value. So please forward my value to that variant. But yeah.
We actually don't support 98, by the way, but don't worry.
OK. I thought it was supported. I just, yeah.
We're dropping 11 soon, so.
OK, OK. So another thing, Spack is a package manager, and I think it's clear to you. We don't try to be a substitute of any build system. Instead, we support a lot of different build systems. Build systems, if you look at packages, comes as base classes. There is package, which is the generic non-specialized. If you don't know which build system it is, or it's a unique snowflake, you can use package, and then you basically have a method install where you need to specify whatever you need to do to install that package. Say you have something that installs using its unique bash script, you can do that with package. It's ugly, but you can do that. Instead, for makefile packages, auto tools, CMake, even Python packages, R extensions, and so on and so forth, we provide basically base classes that automate and contain the generic use cases and the generic workflow. Some of those base classes, I want to point out, like CUDA package, are kind of special because they are not build system. Instead, they are mixins that could be used to enable common functionality. So I don't know if as you can see here, HPX can support CUDA. So it's a CMake package. That's where the build system comes in. And it's also a CUDA package because supporting CUDA means doing always the same stuff. So we have a base class to take care of that in a centralized place. Well, I will be fast on this. The structure of build system is very dynamic. So we use Python. It's a dynamic language, meaning that each build system follows its own workflow. We've seen that basically EasyBuild, I think, showed a step of 17 stages you go through, regardless of the build system. Here, we decided to go differently. Like, we know that CMake does 3 things: CMake, build, and install. But maybe AutoTools does, I think, 4, because an AutoTools package could come without the configure generated. So you have an autoreconf step, a configure, build, and install, and so on and so forth. So depending on the build system, you have different workflows that are typical of that build system. And as you can see, the defaults are, in a somehow abstract way, if you can read this Python code, what you expect. So basically here, I'm saying, OK, I need to build up some options. Where is the root CMake list dir? And I get that path. What are the standard CMake arguments I need to do? What are the CMake arguments that my user wants me to use? Move to the build directory, and then do CMake with all those things. And that's basically what you don't need to write every time. What a user needs to write is just this tiny part, like telling Spack which CMake arguments are specific to that package. OK, this is a tiny detail. The system is so flexible that around its phase, CMake, build, and install, you cannot touch arbitrary code if need be. Like, I don't know, you need to change permissions of a file after the build phase or after the configure phase or whatever. You can do that with decorator. And you can have any function you want as part of your package. And by just saying, hey, run this after install or run this before CMake, that code will run before the phase you prescribed or after the phase you prescribed. It's not a usual need, but sometimes it is. And this is really a lifesaver. And it keeps like the packages kind of clean in terms of code. You might have one function for a single purpose, and you say, run this at the right moment. Finally, how can you debug failing package builds? I would say in 3 ways. You can stop if the build system permits it at an earlier stage of installation. So you can say, hey, stop at configure. Spack will stop at configure, will leave the build directory there, and you can inspect what you think you need to inspect. You can parse the log that have been generated with a command, spack log parse, for errors or either warnings. And I have to make an acknowledgement because this is basically regular expression parsing. And we stole the regular expression shamelessly from the CMake guys. So that's acknowledged in the code, and we basically vendor that. We have a module that uses the same regular expression that were in one of their C++ files to look for that, and they work in a wonderful way. But yeah, if you wonder how can we find warnings or errors, we do like that. And finally, if you need really to go deep, you can stage whatever you need to build, move inside the build directory, and with build-env, you could start a bash with the same environment that Spack would have, and try out things manually. And when you see what needs to be done to fix your build, you write it into a recipe and you retry. So you can
Make.
Yeah, exactly. But you will have the same environment that Spack has when it does the build. So with the compiler wrapper set up and whatever. And that basically concludes part 2. So let's see. OK. Still have kind of half an hour. So if you have questions, please ask. What I wanted to show is just one package, which is HPX, just to show you how a real package, a complicated one, could look like. So here you see we have the package declare. It's a CMake package and also CUDA package. We have a brief description, the home page, URL, 4 version. I don't know if the last one still built, but as you can see, the URL is different from the one that are on GitHub. And then we have a lot of variants with description and so on. And finally, dependency modeling. Oh, one thing that I didn't stress is that dependencies comes into, let's say, dependencies are modeled by edges in the graph. The edges are colored. So dependencies can be of 4 different types, and this is not exclusive. They could be of build type, meaning this dependency is just needed during build. Think of CMake. Link type, test type, or run type. And of course, they can be more than one at a time, like Python, for instance. Here, I don't know if it is correct, the modeling that I made, but it's basically needed for building the thing, because it's required, it's searched for by CMake, testing, and I said running because that's usually the case, but maybe this needs to be corrected. Yep.
If you set something to be only a build dependency and you don't have it installed, Spack installs it, use it to build, does it get rid of that thing after you're done installing, or does it stay in the system?
There is a PR for that. Right now, it doesn't get rid. As you have seen, like we installed CMake, even though I packaged binaries. But there are PRs to do those optimizations. So PRs ongoing for that. Not there yet. But the idea is that, of course, once you build something and you ship it as a binary, you don't need build dependencies anymore. And the other thing, as you said, once you have one CMake that is a build dependency, you shouldn't need to concretize it alongside the other part of a DAG, because you don't, while you care if Boost is compiled with the same compiler that you're using for HPX, you don't care at all if CMake is compiled with that compiler or a system compiler or something else. So right now, let's say we rebuild things which is, not optimized, but it works. But there are PRs ongoing to do those kind of optimizations. And as I was saying, here we declare dependencies, and that's the complete thing we do. Like we depend on gperf tools when this variant is active, and so on and so forth. The last thing that I wanted to show you is the only function that we need to override is this one, CMake args. which is basically returning the CMake arguments needed at configure time. So when you call CMake, and we build those arguments based on what the user requested. So for convenience to keep the code clean, when I wrote that, I also made some sort of functions to deal with a specific part, but the only thing that you need to override is this one. And in the end, you return the arguments, and all the other part of the logic is handled by Spack. And that's because, like HPX, I would say it's a pretty well-done package that follows standard CMake workflow and doesn't need anything peculiar or specific. The only thing that I added out of, let's say, because I found a warning, is this one. Like disabling parallel build, not because HPX can't build in parallel, but because it's like eating a lot of memory. And by default, Spack tries to use all the cores that it has available. And if you're trying to build that on your laptop, it will crash the compiler.
Could we say parallel? So, I don't know where the microphone is now, but we, in general, if you because we have so many templates, the compiler uses a lot of memory, and then the linker as well. And so normally, if you've got like an 8-core laptop, you should never go more than -J4, for example. How is that something you can? Because building in parallel is like you really need it. I mean, it takes long enough in parallel.
Exactly.
So is there a way of saying parallel max for cores divided by 2 or something like that?
There is a way.
It's really a memory thing, but
there is a way to specify it in the configuration. There are PRs that I've been doing basically to limit the parallelism. There is no way, for instance, which would be needed here, to check for other resources and say, hey, I know that roughly I need that much memory, so if you have plenty of memory, go on. Otherwise,
I don't know how you would actually specify the memory, but being able to say use maximum 2 cores on this particular machine, a user option would be a...
But you can specify that from the command line. The point is, if you, you can say Spack install -J whatever.
Oh, well then that's fine then. Okay.
But the point is, if you don't specify it, the default, and if you don't touch the configuration, the default is use every core available.
I could locally change parallel to true, and then just remember always to use
exactly. And we have 20 minutes. So the other thing that I wanted to show you is how to debug things, but I think that we should move on to the development environment. So the idea is, now you have seen how to use Spack basics, how to write packages, what can Spack do for you if you develop software? And we should talk, before answering this question, of a, I would say, relatively new feature, which is Spack environments. And you can roughly think of that as virtual envs, but not for Python, just for everything, like C++ libraries or things like that. So Spack environments are just virtualized instances of Spack that are managed directly by Spack. Why I say virtualized? Because we saw before that Spack installs things in its store, let's say. That store will be unique. When you create an environment, basically you just see part of that store, depending on what you ask for. We have command to create environments, to activate them, to ask what's their status, and to ask what's available in the environment. So that's kind of funny, but during code reviews, we added this line because people trying the branch, they activated an environment, they had a ton of packages installed, and they saw, no, wrote specs, zero installed packages, and they were like, okay, I spent days installing them, where are they? They are still on your disk. It's just that you activate an environment, now you are in a virtual instance that right now is blank. So we added this, let's say, message to the user so that it knows it says 0 installed packages because it has an environment active. As I said, environments are built over Spack Store. So you can install things directly into them. If they are already available because they were installed before, they will be just pulled in. Otherwise, they will be installed in the store and pulled in. And you can set up a group of packages at once. So those are basically your abstract request for the environment, meaning you ask for HDF5 without MPI, for MPI-CH and Python. And when you install, those packs can be concretized separately or together. Together is something that I did, and it's still under review, but I pulled in because it's so useful for software development, in my opinion. And that will be like merged, I think, pretty soon. When you install, you concretize those things, and then you install whatever you need. So what happens underneath when you use this command line interface is that basically you're building a YAML file, which contains, let's say, configuration of all the aspects that you might want, like mirrors, modules, whatever, and also your abstract user request. And in this case, also, if you want to concretize those things together, concretize together basically means everything should be consistent. Like, if anything needs an MPI, it will be just one MPI present in the concretization. If you think of other package managers, like Bundler, that pioneered this model, this is your manifest file. This is your logical request, what you need. Then, the good part about this YAML file is that it doesn't need to live within Spack. You can ship it with your source code for other people to use with Spack and rebuild a development environment on their own machine. Because why not? You say, hey, when you want to build HPX with every, I don't know, instrumentation turned on, use this spack.yaml. You do spack install, you create an environment, you install things, you create, we'll see views within that environment, which are basically links to whatever is in the store to put them in a sort of root-like folder. So all the things together within /lib. I'll show that to you. It could make more sense. I don't know if that was clear. And yeah, that's one way Spack can be useful right now in a development workflow. Whenever you concretize something, Spack also produces a log file, a spack.log, which contains all the information on what is going to be installed right now on this machine. And using either the manifest, the spack.yaml, or the spack.log, you can reproduce an environment. Of course, the spack.log needs the same target, the same OS, and whatever, and you can reproduce exactly this installation. The manifest file, the spack.yaml, is basically your abstract request that should be fulfilled. And I was saying environments come with an associated view by default. You can configure this view, but basically what happens is that, do you remember that I showed to you that Spack installed all the different things in its own prefix path and whatever? If you can ensure that if you have view equal true, which is the default, basically within your environment, you'll get a directory with soft links to whatever you ask to be there, and it will be all in one single folder. Like, views, lib, all the libraries that you ask to be there. Views, bin, all the binaries that you ask to be there. So how can you use Spack environments to develop software? Basically, you can create a manifest file for each development environment that you think it's useful. and you can use this manifest to distribute the environment. You can even put that into your source code. I didn't have time today to show that to you, but you can even build containers out of that. It's kind of easy if you do it in a multi-stage way. You use Spack, you build that dev container, and like using multi-stage or whatever, you can even get rid of Spack itself when it installed stuff and just ship the container with the binaries unit. And on that, okay, that's another thing that I wanted to tell you. It's a pretty new feature. In case you need some specific feature that is not yet there, or Spack fits 98% of your needs, but not the last 2%, you can still extend it with custom commands that could reside completely in another folder or in another repository. Those commands can basically use the core of Spack as Python libraries. There is a prescribed structure that is like mandated and described in the documentation. They can ship with their own test or whatever. In this case, the command is filter, which is not present in the built-in Spack. And the only thing that you need to do is in the configuration, point Spack to the directory containing this extension, and you will have the additional command available from the command line. So this is just, I won't dwell on that. The feature still needs to be polished or whatever, but and it's pretty new, but it's worth to know that if you think there are particular needs that are just for you, for your site, you can still extend Spack and make use of whatever Spack can give to you in terms of internal libraries to do something that could be either very site-specific. And before we go into deployment, let me show the part on development environment. So what I'm doing right now is I'm bringing into the path the newer GCC. So let me check if I didn't mess up this line, because it will be hard to get there again, and I did. Okay, this seems good. Okay, so I have a folder here called HPX development, where I prepared a checkout. Okay, I can make it slightly bigger, of the sources, and a folder called deps with basically a manifest file. This manifest file just contains the dependency that I need: valgrind, Python, hwlock, CMake, and boost with this standard. Okay, not in this case. I'm building with systemmalloc. Okay. And I say concretize the things together. And what I can do is say Spack concretize. It will go through the thing, try to resolve all the constraints. And yeah, the parentheses are a glitch that needs to be taken out. But basically, what happened is that now we produced this spack.lock. And the spack.lock contains all the information on what will be installed and how. And so I can say Spack install and yeah, take questions, because it will take like 1 minute or something like that. But the idea is that now I will install all the dependencies. Then I will activate this environment, meaning I will be able to use every binary that is there. And then I'll copy a very long CMake line, which is what is missing. I will copy it from the script and show that I can configure HPX with whatever I just built. I could also show that I could compile it, but it takes like 20 minutes, even though I turned off all examples. And so, but yeah, it compiles and installs. Yep.
So just to clarify with this environment, so if you set up an environment and you want to install something that's already installed by Spack, then it just pulls
that can be already installed by Spack. So what I mean is that if you have 10 environments and they happen to ask for the same thing over and over, there will just be one installation of that thing.
But then if you request, you have the environment, you request a package that isn't there, will it always install it then to that location, or can it install it to the user's own directory?
Well, it will always be installed where Spack usually installs stuff, and then it will be kind of registered as being pulled into the environment.
Okay, so the use case, let's say, where you manage some cluster system, something, you install some kind of software stack, and then you give the user would be able to install their own software, but they can't install to their own directory package.
That comes later.
Okay.
That's basically, your request is, like, we have user support team. We are not developing. We are deploying for users, but I want users to be able to reuse what I installed or things like that. That comes later. So I'll activate this environment. And now, if I say which CMake am I using, I'm using the one in the environment. And I can go here and do something like make the build, and then cheat a bit, like opening this script that I use to check whatever I'm going to type here. Copy this very long line.
John, you need one option where you say all dependencies are in this directory.
And basically, we are configuring.
Show me the line you pasted in again.
Okay, yep.
Just scroll up whilst it carries on.
Oh, I think it was kind of weird. Probably it will be typed better. That should finish pretty soon if I do arrow up.
I interrupted you. Apologies. You were about to say?
Oh no, I was about to say that it's going to configure with like whatever dependency we have in the environment. So the configuring is done. I chose a random configure, so I don't know if it is like a...
See what it generated that you pasted in, because this is definitely a very useful potential.
So that thing, I did it manually, but we can generate it, and that's one of the things that is like, so let's say development support is something that we started to tackle not so long ago if we compare it with deployment. But these things are definitely known to Spack, and this line is also pasted when you generate module files and you deploy things. We also pass that line into the module.
So what do you mean by you generated it manually? Because it was there in that auto-generated file. That
no, in this case, in this particular case, that's a line that I came up with.
it was already in the template that was auto-generated and copied through. Okay. Because if it, I mean, I'm sure all that information is in there. We could export that, and then you could have a SPAC CMake something, and it would just pump out for all the dependencies. And okay.
That's the idea. So right now, that information is just used to deploy HPX. We have no way to basically give that information to you and help your development outside. But that would be pretty easy, I think, to extract. And okay, and that's what I wanted to show for like software development. I think we are pretty much there. So there is the deployment stuff. I'll try to be kind of fast on that. You developed your thing, you want to make it available to people, or you want to deploy a lot of applications to potential users. Well, Spack.yaml also supports a matrix syntax, so the syntax may vary a bit. This is also another thing that will be merged pretty soon, like in a month or so. But basically, the idea, I think it also, okay, I think it also changed already. I have an example here in deployment. So it's better to have a look at the real syntax. Here, basically, I'm installing 2 versions of HPX. And the way you do that is that each of those lines constitute a matrix. And they build up in a combinatorial way. So here I specify the dependency. Here I specify GCC, and of course, it's only one item. Here I specify 2 different variants. One is malloc equal tcmalloc, and the other one is malloc equal system. And here I just specify HPX with C++ standard. So when you multiply all of that and you take the combination, you will end up with HPX, which is installed with Boost 168 with this compiler, but on one side with tcmalloc, and on the other side with systemmalloc. And you could like extend that, and you could add 2 compilers, and you can start to build a lot of combinations out of that.
Yeah.
And yeah, so basically why I pasted the thing here, because think of this case, like where I have a lot of things that I want to be installed with GCC 5.4. Basically, I don't have to repeat every time I want them installed with GCC 5.4. I just put them on a single line and say the compiler is just that one. So you can split your specs and let be recombined like that. And here I have just a configuration for modules for this deployment. And well, what I can do right now is, while we talk, I'll try to show you the last bit, which is the concretization. So let's do, let's say, we should leave like Spack alone while it concretizes and proceed with the rest of the thing, which hopefully are not that much. What I wanted to say, if you deploy on HPC clusters, you can, of course, generate module files. And those are highly configurable from YAML configuration. The way that module files are generated, they are basically generated as from templates, from Jinja 2 templates, which can be configured. And they are generated from an inspection of the installation prefix. So they are just a byproduct of an installation. When you install things, they could be automatically generated by a post-install hook. So you say Spack install HDF5, there will be an hook if you configured some module file generation that runs after the installations, inspects whatever is in the installation prefix and produces the module. Or they can be just regenerated on demand from the command line. And yeah, the module file is kind of super flexible. You can do whatever you want up to the point that you can completely change the Jinja 2 template that is used, or extend it, or do things like that. And if you click here, you have, I would say, a 1 hour something tutorial that covers everything that you can do yourself. Okay, that's another part that I said. We have command line tools to manage module files. So you can say module tickle refresh just this module tickle remove just this module, or module tickle refresh everything because I changed something that impacts all modules, and you get all the modules rewritten for you with a new features or with environment variables added or removed or things like that. OK. I'm trying to do two things at once because, yeah, we are short of time. Here I'm installing basically the metrics of things that we've seen before that we wanted to deploy. And now, another feature that I wanted to tell you. You can maintain site-specific repositories. When you download Spack, within the source code, there is the built-in repository with all the 3,000 recipes that you have seen. But if you have custom things, or if you want to tweak some built-in recipe, you can do that. You can create a new repository, and you can have whatever you want in there. You can even inherit from built-in recipes and just do small modifications. And then all the packages are namespaced. So basically, you have to use the name of your repository dot the name of a package to access a specific recipe. And depending how you set up Spack, you give priorities to repository. And if you don't specify the namespace, the first repository in which a package is found will be the one that will be used. That's as simple as that. OK, I think this is like what you asked for. So can I reuse what is installed in another Spack instance? This is a feature that has been merged back in November. It's useful at HPC sites. It's called Spack chains. We have seen that Spack stores all the information of the software that is being installed in one central database. And with this feature, what you can do is clone your own Spack and configure it to use another Spack instance installations as read-only things. So that if you ask to install something and it was already installed in the other Spack instance that you registered, that thing won't be, like you won't install it into your own instance, but just reuse the one that you found. This is kind of abstract. When is it useful? In my opinion, it's extremely useful at HPC sites because you can maintain entire facility installations of the software that is used by everybody in the most common configurations. And then you can have hierarchies. I would even say different level of stability. What is provided by the site should be like rock solid. You should rely on it, and it should be useful to everybody, unless you want to clutter your environment with its specific request that everybody sees, but just one guy uses. On the other end, departments, for instance, which might be interested in, I don't know, a specific area, could register the site database and build on it the software that is used just internally to the department. And you can like go as deep as you want, up to the single user that has like 2 or 3 Spack instances registered. And he can go on with experimental builds of his own software that he will probably just use, but he will be able to reuse whatever was installed at site level. So that's a relatively new feature. I hope it does answer to your question, how you can reuse installations. OK, so before we go to what's on the roadmap, yeah. So what I did here was, if we go back, to install all those things that are specified in the metrics and generate the module files for them. lmode refresh -y -delete 3. And the last thing that I wanted to show you, when Spack will be finished regenerating the lmode module files, is how you can deploy. In this case, I set up a very simple environment with just one level of hierarchy, which is the compiler, and I provide 2 versions of HPX and a few other things there. So it's bwd dot spack, well, sorry. That's like the entry point for lmode. So I basically generated module files in this directory automatically within my view. And I can start using them. If I do module available, this is, of course, just a demonstration. You just see, as in a usual, how many of you are used to lmode hierarchies? OK. So basically, lmode permits you to lay out module files so that they are visible only if, let's say, the relevant package in the hierarchy that enables them is loaded. So in this case, I just have things which are compiled with system compilers, including the GCC that we bootstrapped. When I load that compiler and I type available, I see all the software that has been built with it. And I see 2 versions of HPX, one with system malloc and one with tcmalloc. And if I ask module show HPX to see what's in the generated module, I have a lot of information, including the configure options that have been used to build this HPX. And of course, this is kind of, let's say, realistic, but still toy example. But you can fine-tune this thing for your site and put all the information you want there, all the different version of HPX or whatever software you want. And potentially, the idea is that you can describe in a single file the entire deployment that you do at your site. That's basically the potential of this kind of syntax. So with this, I'm pretty much done with the demo. And I just have like a few notes on the roadmaps. So this one is just an image for something that we already discussed. We would like to build infrastructure to serve both sources and binaries. The way it works right now is that a user issues a pull request, it's checked in on Travis, and that's it. The idea is that Travis should verify the checksum of the new version and put them somewhere in a mirror. And that's the easy part, because basically we have everything needed in software to do that. I just did it locally. We just need somebody to pay for the mirror in the cloud. And I think it will be like Livermore or DOE through some grant to do that. The other part, which is slightly more complicated, is to have, let's say, continuous integration scripts that build binary artifacts for widely used configurations of common packages. I don't know, compilers, MPI, whatever. Either on, let's say, common HPC clusters like ours, or on top-level machines, which could be the one hosted at CSCS, through this modification that I said of the setuid GitLab runner, so that you don't have security issues. And the other thing, which we already talked about, is we want to have a better detection of the host, a finer detection of the host, and a better handling of cross-compilation. And those things will basically proceed, I think, together. As we decide how we want to detect the host, we will also try to build up some sort of mapping between some host, a compiler, and the optimization that needs to be turned on to target that specific host. And finally, this seems kind of simple, like pictured like that. but we want to change our SAT solver to take into account also what's installed and the binary packages. And this is an enormous effort that is ongoing. And I don't know when it will land. I know that Todd is working hard on that. But yeah, it's pretty complicated. I think that he wants to turn to a CDCL algorithm for SAT solving, or at least that was the idea. And you know, whenever you go to complete algorithm, you want to have both something that is accurate, but also something that doesn't take forever to compute. And that's the hard part. And I'm pretty much done. So thank you very much for remaining here, even though I am like a quarter of an hour late. And if you have additional questions, I can try to answer them.
Just for clarification, so I have to go with an example. Petsy and Trilinos, they both depend on each other. So you can build Petsy with Trilinos support, you can build Trilinos with Petsy support. So
okay, that I didn't know. Circular dependencies.
Yes, which is super beautiful. So you need to bootstrap the whole process, right? So you start with building Petsy first, then you build Trilinos with Petsy support, then you rebuild Petsy with Trilinos support. That works with Spack, or?
That's too specific for me to say. I would say, I mean, I never.
So can I first install?
I would say that circular dependencies are not working.
Okay.
So they are forbidden because, yeah, A that depends on B that depends on A doesn't work much. And we do.
Create a dummy SPAC config for the first.
Exactly. What would be done in that cases? There are, I think, cases like that to bootstrap. Like, I think I need to have a look at that. But I vaguely remember that to bootstrap Go support in all the GCC compiler, they did something like that. Mm-hmm. They had a dummy package, which was just needed to bootstrap the thing, and then the real one. I don't know if the guy that are basically maintaining the exascale computing project software, because those two will be part of it, right? Mm-hmm. Are like working on something specific to address this issue. But that's worth like asking either in the Slack or looking at the issues.
And then the same question as yesterday for EasyBuild. What about source code repositories to build directly something non-versioned yet?
Source code?
Built from Git repository
directly. That's possible. That was shown. You can say Git is here. Yeah. Version develop is tied to branch develop, or version develop is tied to this commit hash or to this tag. Yeah, you can do that already. Okay. You can do that for Git, for Mercurial, for.
So the formula for it doesn't need the checkdown. It's just the Git URL.
Sorry?
The URL is just the Git repo.
So the URL usually is the URL of the tarball. And you have another attribute, which is called Git, in case of a Git repo, which is the Git repo.
And if I prefer to have URL master.start instead of using the Git repository, I use the master. And can I generate this function? Could I generate?
So if it is a valid URL, like something that you can do, I think via REST or something, probably.
The checksum is not required?
No, it's not required if you are on master, and that's why it's discouraged, and that's why you won't be able to install those things like on system where they care a lot about security. I don't know. At LLNL, I doubt you can install anything you want if it is not checksummed. But still, you can do it if you want to do it on your laptop or on your cluster because you are permitted. But of course, you can't checksum master because master is moving. You can't checksum a tag because a tag is moving.
I only have a final comment, which is that does anybody else actually run modules on their laptop? Because that's I didn't think I needed to until watching this, and now I think
No, but
I need modules on my laptop now.
Really?
It's like
that was meant to
creepy. It's like,
that was meant to exemplify how you can like deploy at a site. But yeah.
okay, that was much more interesting than I expected. So thank you very much, and thank you especially to Hannes and Lucas for the work you put into the CMake, and for all of you guys for attending. That was for, and Theo here as well. Thank you. And we wrap it up there. And thank you, Lutz, for looking after us. And if anybody wants to quickly pop upstairs and look through the window and see the machine, I mean, we can't go in, but we can at least point to it and tell you about it. So thank you again, and that's the end.